This will be our first video in our Calculus 1 series. So let's go ahead and get started with a review of our prerequisite material for Calculus 1. And this will be an outline for what we're going to talk about today. First, algebra and functions, and we're going to talk about a catalog of essential functions, then transformations of functions, inverse functions, function algebra and function composition, and then rules of exponents and logarithms. Then we'll come back and talk about some geometry and trigonometry with linear functions and a review of graphing. We'll add to our catalog the equation of a circle and trigonometric functions. We'll specifically talk about the unit circle, which is here. And then we'll also talk about some inverse trigonometric functions that will be important to us in calculus. But let's get started here with our catalog of essential functions. And the first is going to be the linear function. I'm going to do my best to draw this by hand. You should have these in your textbook in the back. Actually, let me see if I have this here as well. So here it is. Excellent. So here's the library of functions that we're going to talk about. And our first one is going to be the constant function here, which is going to be f of x equals b, and it goes to the point 0b, and it has a slope of 0. Its domain is negative infinity to infinity, and its range is just the set b. Then we have the identity function, which is what we were just about to talk about over there as a linear function, f of x equals x, and it looks like the function over there on the right. It has a domain of negative infinity to infinity and a range of negative infinity to infinity. And the end behavior here is going to be similar on all odd powered functions, like this, where a power function is in the form of x to the n. And then we have the squaring function here, the quadratic function, f of x is equal to x squared. It has a domain, again, of negative infinity to infinity, but its range is going to be closed with a minimum at 0, and it's unbounded at the top. All even power functions generally have this kind of a shape here. And then the cubic function, f of x equals x cubed. All odd power functions generally have that kind of a shape there. It has a domain of negative infinity to infinity and a range of negative infinity to infinity. And you see that it's going to have this special point that we're going to talk about in calculus later called a point of inflection. It's decelerating here where the slope is increasing but at a decreasing rate, and then it kind of levels off here, and then it's going to start increasing at an increasing rate. It's going to decelerating, then it's accelerating, and we'll find out how to find that point there with calculus later. The next one is going to be the square root function. F of x is equal to the square root of x, and you need to pay attention to the fact here that this is wrong for the domain. The domain here is 0 to infinity. Because we're not allowed to stick negatives inside of the square root sign there. So that was a mistake from the textbook publisher that wrote that. So here we go. We start at its vertex at 0 and go to positive infinity here. The cube root function here is going to be another one. When we talk about inverse functions, this is the inverse of the cubing function. This is the inverse of the right half of the squaring function. We'll talk about that later. The next main one here, f of x equals 1 over x. We have these asymptotes here. At y equals 0 is a horizontal asymptote. X equals 0 is a vertical asymptote. We're not allowed to divide by 0. So we have negative infinity to 0, union 0 to infinity for both our domain and our range here of the reciprocal function. And then we have the squared reciprocal function will also be important. And this is any negative odd power function here, or if we have 1 over x to the n and n is an odd power, it'll look something like this. 1 over x to the n, where n is even, will look kind of like this. And it's going to go from negative infinity to 0, and then from 0 to infinity. And it has a range of 0 to infinity. Still has the same vertical and horizontal asymptotes. This is just going to be in quadrants 1 and 2 instead of quadrants 1 and 3. We also need to know about the absolute value function. There's a couple of different ways that we can define it. One of them is piecewise defined, and that helps us a lot in calculus to think about it that way of x, if x is greater than or equal to 0 and negative x if x is less than 0. Its domain is negative infinity to infinity, and it has a range of 0 to infinity. The sharp point here is going to be called a cusp in calculus, but you may also call it a vertex right now. And the other way to define this is f of x is equal to the square root of x squared. That's also the same thing as the absolute value of x. So we might need that definition occasionally as well when we deal with a square root of something squared. It's going to be the absolute value function. That'll explain more why we have to restrict the squaring function to only one side to get the square root function as its inverse. Exponential functions are going to be the fastest growing functions that we're going to talk about in Calculus 1 right now. And some people will call them a hockey stick graph, but they are what we call monotonically increasing or monotonically decreasing. You're always doing the same thing. We always have a negative slope or we always have a positive slope here. They're going to be in the form of a to the x or e to the kx. E is a special number. We use the letter E because it's named after this guy whose name started with an E, Euler. But we call it the exponential number sometimes. You'll recognize it from things like continuously compounding interest, where A is equal to PE to the RT, something like that. And we'll speak more about that, about what the definition of E is later when we get to some limits. But the domain of an exponential function is going to be negative infinity to infinity. And it's always going to have this horizontal asymptote down here at y equals 0. And it's going to really have that asymptote only on one side. It'll be on the negative side if it's a rising exponential function, and it'll be on the right-hand side if it's a falling exponential function. The natural logarithmic function is the inverse of this exponential function, the logarithmic function in general, but we're going to look at the natural log, which is going to be the inverse of that e to the x type function. And it has a vertical asymptote here at x equals 0. This is going to be the slowest type of growing function, and this is going to be the fastest growing function. That'll be important to us later. Its domain is going to be 0 to infinity, and its range is going to be negative infinity to infinity. And we'll come back to these trig functions here in just a minute, but I've actually just used that to talk about all of these types of functions and a couple more that are important to us. So let's go ahead and let's look at transformations of functions. Recall for constants a, b, c, and d, and for a function f of x, that we can write the general form y is equal to a times f of b times the quantity c x minus c. close the parentheses for f of x plus d, where a scales the function vertically. It's a vertical stretch shrink. We call this a dilation. Like your eye dilates, it can get bigger or smaller. If a is less than 0, then it's also going to give us a reflection across the x-axis. B scales the function horizontally, so this is going to be usually a horizontal compression or stretch. Compression if b is greater than 0 or greater than 1. A stretch if it's between 0 and 1 for the absolute value. If b is less than 0, then we're going to flip over the y-axis. C is going to shift left and right. This is a horizontal shift or horizontal translation. And this is a vertical shift or a vertical translation. So translation and shift are the same thing to you. We just, and these are rigid transformations here. Rigid transformations, meaning that it doesn't change the shape of the graph when I move it horizontally or vertically. Reflections are also rigid transformations, but dilations, stretches, and compressions are non-rigid transformations. All right, let's go ahead and let's sketch the graph of negative x minus 1 squared plus 3. So first, let's identify our a, b, and c. So a is a -1, b is a +1. There's no multiplier in there in front of x. C is also a +1, and D is equal to +3. So there's no compression, no horizontal compression or stretch. What that tells me, we're going to reflect over the x-axis here. So what that tells me, we're going to shift 1 left there, or I'm sorry, 1 right. And we're going to shift 3 up. Okay, so going to take our characteristic points and give a new vertex at 1, 3 there, and where we normally would go 1 right and 1 up to get to the next point, we're going to go 1 right and 1 down because of this negative here. So 1 right, 1 down, 1 left, 1 down, and it's symmetric about this axis of symmetry. X is equal to 1. And if we go 2 right, we should go 4 down. So 1, 2, 3, 4 should be like this. Like so. And that should be our f of x. And our new vertex, like we said, is at 1, 3. All right, again, that was just a recap. That's not supposed to be a full lesson on that. If you need to see more about that, you can go back and view my pre-calculus videos. There's plenty of that. Also, look at the Apex pre-calculus videos specifically, and they'll have lots of examples on this as it covers a lot of these prerequisite topics. before coming into Calculus 1 that are important, and it's going to go through all these things that we're talking about here. So let's find the inverse of f of x is equal to x plus 1. So first, let's solve for x in the problem. If this is y equals 2 over x plus 1, then x plus 1 equals 2 over y. Let's actually do that through cross multiplication so that you can see what I did. So this is y times x plus 1 equals 2 times 1. Y times x plus 1 is equal to 2. X plus 1 is equal to 2 over y. X is equal to 2 over y minus 1. And then we want to switch our x and y here. So this is f inverse of x is equal to 2 over x minus 1. And check using a composition of functions. F of f inverse of x should be 2 over x minus 1 plus 1 is 2 over 2 over x is 2 over 1 times x over 2 is x, and f inverse of f of x is equal to 2 over minus 1, and this is 2 over x plus 1 is equal to 2 times x plus 1 over 2 minus 1 is x plus 1 minus 1 is equal to x. And so both are true, so they are legitimate inverses of one another. Graphically, if we were to look at this, they would reflect over the line y equals x, the identity function. That's why that one's so important in our library of functions. So just a quick sketch here, going to put the broken line here, y equals x, as it's not actually part of my graph. And I'm just going to give an example of two functions here that are inverses. For example, y equals e to the x. It's going to look like this. Horizontal asymptote y equals 0 here. Y equals e to the x rises like that. Then we get the point 1, 0 over here, and I'm going to have this vertical asymptote here, and this is going to be y equals ln of x. And I want you to see that this xy switched to yx, or the x and y coordinates switched. So 0, 1 became 1, 0, and vice versa when I reflect over the line of y equals x. That's what makes things inverses graphically. So if we have the function here that we want to f of x equals 2 log base 3 of x minus 1, and we want to find the inverse, then let's solve for x. Or if you're used to it, I'm going to use another method here. I'm going to switch x and y and then solve for y. Let's see. Yeah, I'm going to switch x and y. Solve for the new y. Replace y with f inverse of x, and I'm going to check my domain and range when I'm done, because the domain of the original should be the range of my inverse, and the range of my original should be the domain of my inverse. So let's switch x and y here. Solve for the new y. This is 3 to the x over 2 is equal to y minus 1. Y is equal to 3 to the x over 2 plus 1. So f inverse of x is equal to 3 to the x over 2 plus 1. And just to check here, my original domain was x needs to be greater than 1. And my range here would have been y is between negative infinity and infinity. It's just any element of the real numbers. So let's do that in function or in interval notation. This is 1 to infinity, and this is negative infinity to infinity. My domain of my inverse function should be, yep, x is allowed to be anything. And my range of my inverse function is that y has to be greater than 1 because I have that as my horizontal asymptote. So 1 to infinity, and they definitely did switch places. All right, let's look now at function algebra and function composition. I did a little bit of this when I was proving inverses just a minute ago, where I stick a function into a function, and that notation is going to be f of g of x, either written this way or this way with the little open circle. So let's find f of g here, where g is the inner function and f is the outer function. We write our outer function down first and put our inner function inside here. Then we're going to write x plus 2 times x plus 2 to deal with that exponent. Don't just distribute the 2. We're going to have to FOIL here. X squared plus 2x plus another 2x plus 4 plus 1 is x squared plus 4x plus 4 plus 1 is 5. So let's also remember that if I have a plus b squared, it's simply a squared plus 2ab plus b squared. And if I have a minus b squared, that's a squared minus 2ab plus b squared. Calculus, we don't want to make those mistakes of how to square a binomial. We're going to be doing it a whole lot. We're going to be completing the square sum in calculus, and we're going to need to know how to go from this right-hand side to this left-hand side. So that's something that we want you to know. Let's look at another example here where we find an expression for f of g of x, given that the big function that we're trying to get here is the square root of x plus 2, and g of x is equal to, I'm sorry, we're not decomposing. F of x is equal to the square root of x plus 2, and g of x is equal to x squared plus 1. Decomposing is something we'll do in a little bit, but if we want f of g of x, then that's going to be square root of something plus 2, and g is x squared plus 1. So we get the square root of x squared plus 3, like that. We have to leave it like this. We can't break this up anymore because that's a plus sign in there. We only can break up that square root if it's a minus sign. If we were going the other way, and we will have to decompose functions some in calculus to find inner and outer functions and look at them as compositions. Let's say that I started off with something like the square root of x squared plus 3. I would want to say that I could write that as f of x is equal to the square root of x, and g of x is equal to x squared plus 3. And I could write this as f of g of x that way. That's going to be important for us to know how to do that. Okay. So rules of exponents that you're going to want to remember here are that when I multiply like bases, I add the exponents. When I divide like bases, I subtract the exponents. When I raise a power to a power, I multiply the exponents. And when I have a negative exponent, I want to take that across the fraction bar to make it positive, and any nth root is going to be the denominator of the power here. So the nth root of x to the a is going to be x to the a over n. These are all going to be important rules for us here in a little bit. So let's go ahead and practice our rules of exponents and simplify the following expression. So let's work on our numerator as x squared yz. And down here we get x cubed y to the third z to the 12th. Now we're going to take the smaller power to the bigger power like this. And we get ones left up top as placeholders. So 1 over x to the first, y to the second, z to the 11th. I put lines through my z's here just so that you can see that it's not a 2, because my 2's and my z's look a lot alike. All right. Laws of logarithms are based completely on those laws of exponents. So we're going to, this is an equal sign. We're going to rewrite. A is the base, and in this case, y is the power. The logarithm is the power here. So a to the y is equal to this argument x here. And so you can rewrite back and forth. We can use this thing called the triangle of power if you would like to. See an example here. I'm going to put 2, 3, and 8 in there. We can write this as 2 to the third equals 8. We can write the cube root of 8 is equal to 2. And we can write log base 2 of 8 is equal to 3. All three of those statements are the same relationship, written in different ways depending on which box in the triangle of power we are looking at. So you may know other names for this, but this is just typically what I use in tutoring, is the triangle of power with those three boxes. Which two boxes do you have, and which one are you trying to solve for? So if we have our base here, and we have our power here, and we have our answer here, let's call this E. Some people call it Ben, B-E-N. So we have our base to our exponent is equal to n, like that. We can have log base b of n is equal to e, and we can have the nth root of we need this, the nth root of n is equal to b. It's going to look a little strange because usually we have nth roots, but just these three things are what I was writing over here. Okay, since logs and exponentials are inverses of one another, when I compose them, I get x here for all x's. It doesn't matter whether I stick a exponential with the same base within a log, or a log of the same base within an exponential. They'll undo one another. Watch out, this is true for all x. This is only true for x greater than 0 because of the restriction here on the log function. When I multiply inside a log, remember when I multiply like bases, I add the exponents. This is addition of exponents over here. So this is because a to the x times a to the y equals a to the x plus y. It's the same rule, just written a different way. This is because a to the x divided by a to the y is equal to a to the x minus y. And this one is because a to the x raised to the r, if we're going to use r here, is going to be a to the xr. I like using y here and saying xy. This is the same rule as before. Remember that we also have anything to the 0 power is 1 as long as a is not 0. Anything to the first power is itself, which means that log base anything of 1 is always 0, and log base a of a is always 1. Those are important things to know as well. Let's go ahead and come back to our geometry and trigonometry in our next video, and we'll stop this one here. See you for the next video.